today what I thought I would do is just talk about some new ideas in biology that gives a little broader perspective than maybe many of you would have coming into university. So many times students come in and they're doing biology because they're interested in medicine or pharmacy or dentistry is one of the common routes that they go in, and maybe don't think of some of the other options. So I don't want to make this a long, sort of tedious kind of wordy lecture. I just want to give you lots of examples. And even coming here, I was thinking of more examples, and we'd never get out of the room if I really got going here. So what is biomimicry? It's the intersection of biology and technology. And it's not new, but it's kind of getting some new life as a whole new group of people are starting to look to biologists for answers. And I was at a conference a couple of years ago on biomimicry, and I thought, it's going to be all the biologists sitting there patting themselves on the back with their great ideas. In fact, the majority of people at this conference were architects, landscape architects, industrial designers, engineers, pretty much anything but biologists. We were in the minority, and they were just trying to make connections to solve some of the problems that they were needing to consider, and in ways that would be new, novel, sustainable, workable with nature. So one of the people that's really started to promote biomimicry in recent years is Janine Benyus, and she wrote a book a number of years ago now called Biomimicry, Innovation Inspired by Nature. So I sort of reworked her title today, so there was nothing particularly novel in that either. Biomimicry is a new way of viewing and valuing nature based not on what we can extract from the natural world, but what we can learn from it. So all too much of what we've been doing over the last couple of hundred years has been extraction. Resources, fossil fuels, water, anything we can get out of nature with little view to what the impact might be. This is saying, let's look at nature and see what it can teach us about dealing with the need for resources, but also how to deal with the waste. So it's derived obviously from the word bios, for life, and mimesis, which is the word for imitating. So it's all about working with nature instead of the other options that we've been dealing, or approaches we've been taking. And the idea is to come up with long-term solutions to many of our issues, from very little things like new materials to big things like climate change. And we can imitate nature in our designs, in our processes, in our bigger systems. And I'm going to focus today mostly on some of the materials and technologies that are being developed and indeed are already in place. And you may not even be aware that they have biological parents of a sort. So when we say learn from nature, the idea is that humans are pretty new to this planet. And life is very old on this planet. It's been around for about 3.5 to 3.8 billion years. And there's all sorts of organisms that are still around, like the bacteria, that are extremely successful that we can learn from. And other groups like insects that have been around for a long time that we can learn from. So this diagram, and it's probably not showing up very well for you, but the idea is if we were to take the whole history of the planet and superimpose it on a one-year cycle, we can get some interesting ideas about how new we are to the planet and how much other life has been here that has solved problems through trial and error and probably has suffered from far more serious problems than even we are facing currently. So if you take that the January 1st is when the Earth first formed 4.5 billion years ago, then life appeared around 3.8 billion years ago. That's sort of the current number. That makes February 25th, or next Thursday, life's birthday on this planet. So remember that next Thursday. And then we can go through all sorts of organisms. As they developed into March, we had the development of multicellular organisms, and then we have fungi and fish and land animals. Humans don't appear until about 30 minutes before midnight on December 31st. So we're the new guys. And all these other life forms have figured out ways to work with nature, be part of nature, and contribute. So Janine Benyus has presented a number of principles in biomimicry, and these are just some of the basic principles that we teach you and that you're learning in biology. Nature runs on sunlight. Nature uses the energy it needs. It fits form to function, so that structure-function dichotomy works really well. If you know something about the form, you know something about the function, and vice versa. Nature recycles everything, so there is no waste in nature. And everybody's waste becomes somebody else's treasure. And if we take that kind of idea, we would not be throwing things in landfills as we do now. Nature rewards cooperation. There's tons of examples where species get together in symbiotic or mutualistic relationships and work together to make a world for themselves and a better world for other species. It banks on diversity. So one of our big concerns right now is loss of diversity. So we're going against nature by losing a lot of probably very important species that we don't even know exist, much less what they do. Nature demands local expertise, so everybody has a role to play. It curbs excesses. If you overuse resources, you won't be around for too long. And it taps into the powers of limits. It takes everything to the limit, but doesn't exceed that. So it works within the constraints that the planet sets for life on Earth. So I just want to go a few examples here. I'm not going to go into a lot of the details, but one thing I want to point out is that too often in biology currently, we focus on two processes, bioprocessing and biotechnology. And a lot of times we learn biology with that idea in mind, not thinking so much about the biomimicry. So in bioprocessing, we use natural materials or processes. So we use things that organisms already make, or we use processes that they already carry out. And then, of course, most of you are more than familiar with biotechnology, where we're actually changing life by introducing new genetic material from one species into another that would not normally happen to generate new products and processes. So just as an example of bioprocessing, this is when we use nature to do a job for us. So we put bacteria in sewage treatment ponds to break down organic matter. That's what they do. And we're just giving them a happy place to solve a problem that we have before we release the treated sewage into local waterways. And for thousands of years, humans have been using organisms as bioprocessors without even knowing what the process was. So you think about it, all the staples of life, bread, wine, beer, and cheese, we've been producing through processes like fermentation. Nobody understood what that was, just somebody lucked out and stuck some sugar and they happened to have some yeast in there, I guess, and sealed it up, and all of a sudden there was good stuff coming out at the other end, and we just learned how to do that. So that's using natural processes. We're not modifying, we're not changing anything, but we're taking advantage of what some organisms can do naturally. And in subsequent period of time, we've learned what that process is. Biotechnology, there's a lot of focus on this now, where we're actually changing nature. We're taking genetic information from one organism and sticking it into another organism to carry out something we want done. So we find the gene for human insulin and we put it into bacteria like E. coli and get it to produce insulin for us. And it's actually better quality than some of the ways we've done it before, but we are manipulating organisms. E. coli would never normally be producing human insulin. So there's a lot of interest in doing this and a lot of push and a lot of research being done in manipulating organisms in this way. But in a way, it takes the notion that nature needs some fixing. We can make it somehow better or better suited to us. And biomimicry is different than that. Biomimicry gives us a whole different perspective because it has us working with nature. Let's look at what species do in a bigger picture and how they deal with coming to terms with the constraints the planet provides. And just as one sort of example of this, we can take something like stainless steel, which is clearly a very mechanical, chemical, physical process. It involves extracting materials from the earth and processing them through refining, and then ultimately things like the smelting process to produce a substance that's really, really strong and really durable. And is really trendy if you have to buy stainless steel appliances these days. But these kinds of technologies that we've used traditionally are very often based on a heat, beat, and treat kind of process. You heat things up to very high temperatures to melt them, then you bring them together. Sometimes you have to add a lot of chemicals, sometimes you have to beat it in very physical kind of treatment. So it's physical, chemical, high energy consumption. That kind of industrial process is very energy demanding, so that brings us back to energy issues, and not necessarily super efficient for what we get in the end. And more importantly, there's a lot of waste comes out at the other end, chemical waste and the damage to the environment in extracting the materials in the first place. So how about thinking about other possible options and maybe looking to nature? Well, it turns out that there are spiders that can produce silk strands for their webs that is unit for unit as strong as, or has the tensile strength of stainless steel and is stronger actually than stainless steel and Kevlar. And there's a lot of work being done. If we could figure out how to get that silk produced in sufficient quantities, we could make protective vests for police and military, lighter weight, better product than some of these other materials that we're using. So one option would be just to grow a lot of spiders and try to get all that silk. Not super practical, so that would be just using them to do something. We already have used biotech. We've taken the gene for making spider silk from the spider and inserted it into a goat. And now the goat milks silk. But you get such a tiny little quantity of silk out of the milk that it would take a lot of goats. And that, again, is very energy inefficient and land consuming, etc. You can still use the goat's milk, by the way. It's apparently just fine to use. But what if we could actually understand how the spider makes the silk and go to the molecular level and see the process the spider uses to make this really strong material, and then mimic it? We're not using the spider directly, we're just using the technology the spider has evolved, and going in and working that level at a molecular level. So we're still working on that one, actually. Spider has a lot of tricks up its sleeve making this material. But there are lots of products that are already in use or to some degree in prototypes at least. So I just want to go through a few of these of some of the examples that where we've learned from nature and we use it sometimes every day, or will be in the very near future. So the classic example for biomimicry is Velcro, and it's been around for quite a while. How many people have walked their dogs in the woods and come home covered in burrs and had to get the burrs out of their dogs and their pants and everything and just been annoyed? Well, you just have to have one person a few decades ago start thinking about this and going, you know what? That's kind of neat how that burr sticks to my dog's hair or my pant leg, and I wonder if we can do something about that. And so here's the burr. It's from the plant Xanthium, and it has a really neat attachment process, essentially, so the seeds, the burr, travels around and gives a possibility for the seed to germinate elsewhere and establish a new plant. So it's a reproductive strategy for the burr plant, a nuisance for walkers in the woods. But when this was developed, it became a godsend. Think of how often you use Velcro. I know I've got my power cord tied up in Velcro up here somewhere, and we use it all the time, your boots, your clothing, and it was a godsend for the space age for tying things down in space where everything floats away. So that's probably the first original example most people can think of. But there's all sorts of specialized fabrics that we're developing now. Look to the shark as an example. Shark are very, very fluid in their motions in the water, and so people started looking at shark skin and ultimately developed a shark skin bathing suit that got Olympic swimmers like Michael Phelps in trouble in the Olympics because he was breaking every record, and all he did was had a new swimming suit based on shark skin. So it makes it much more easily movable in water, in fluid environments. But shark skin's also really important. Sharks are some of the oldest animals. They've been around for about 400 million years, and until now they have been pretty successful. Now they're threatened mostly by us, and it's, you know, kind of an indictment on us that we would take out an animal that's had such a long lifespan. But one of the tricks that, or one of the interesting things about sharks is not only do they have this really fluid skin, but they've also got a skin in which no bacteria will adhere. So their skin surfaces are bacteria-free. So they don't get a whole lot of bacterial diseases. So now people are looking at shark skin for another possibility, and that's down in the bottom corner there, trying to mimic shark skin and use it in hospitals on surfaces, because you wouldn't have to use any antimicrobials or bactericides, and we can keep it bacteria-free. And we know now in our hospitals we have serious problems with antibiotic-resistant bacteria doing very well. So here's a possibility giving us clean surfaces without all those antibiotics that are less and less useful these days. A new one that's just coming out is dealing with food wrappers. Huge source of garbage, okay? All hit the fast food places, and there's always paper and plastic. Well, how about we think about what nature does? Look at how many things, like apples and oranges and bananas, they come in their own wrapper, and it's biodegradable. So some companies in the United States have developed a bacterial or biodegradable wrapper for all sorts of things. So your hamburger could be wrapped in a material that is biodegradable, but based on carbon. So you got two options. You can throw it in the garbage and it can be composted, or you can eat it. So you could actually eat the wrappers, just like you eat an apple skin. Just wipe it off. It could be used that way. And this is starting to be marketed in Europe already. So they literally, put foodstuffs, hamburgers, anything like that that comes in all those plastic containers, put it into something that's biodegradable or even edible itself. Another classic one is the bullet train. The bullet train was developed in Japan, and the whole idea is it could go really fast. Problem was, when it goes really fast, especially through tunnels, it creates a sound wave in front of it that would break the sound barrier. So if you lived near the train and a tunnel, it was a pretty annoying day, because these trains are going all the time. Now, it happened to be that one of the engineers on the bullet train was an avid bird watcher. And he noticed that the kingfisher is a bird that can go from air to water and catch fish. But in doing so, he doesn't even hardly disturb the surface of the water. That way the fish doesn't see him coming, and he gets a meal. And he goes in, and it's very, very, it's one medium to another without too much disturbance. So he went back to the manufacturers and came up with a totally new design, which literally does no longer look like a bullet, but looks like a bird's beak. And what this did was it reduced the noise, so that was the first goal, but it also made the train 10% faster, 15% more energy efficient. So a whole bunch of things came out of that by just looking to how do birds go from air to water. And now these trains are breaking speed records all the time, quietly and efficiently. Geckos, fun animals, ones that can climb walls. Mystery, how do they do that? Engineers and military people especially were interested in finding something that could climb a wall. I wanted to mimic that. You could co-opt the gecko, but put a little sensor on it or something, but that's not copacetic at all. But you could try to mimic that. So if you look at the feet of a gecko and look at it really closely, you could actually end up mimicking this in a robot. And now there are robots in trials at various stages that can climb walls. So this has obvious military interests, but also for search and rescue examples as well. And then there's the rough transport vehicles, transporting things around rough terrain. What have people done historically? They use donkeys and mules and horses. They're very sure-footed, alpacas, etc. Sure-footed animals. What if we could mimic that? It'd be much more efficient than the tanks that we are currently using. So there's a company in Boston who's already done this. So this is sort of mimicking a horse. They're doing all sorts of other animals as well. They've mimicked a cheetah surprisingly well. So those are ones that are in use or close to being in use. And the last few I just want to mention are things that might be used to solve our big problems: energy, climate change, and finding sustainable solutions. So we can look at better fuel efficiency. This is always a big deal. And with the car show going on right now, that's one of the things they're touting is better efficiency. Well, Mercedes was looking for new ideas, and they looked at the boxfish, which at first glance doesn't look all that fluid dynamic, I guess, or aerodynamic. But in fact, when they built a car that mimicked the shape of a boxfish, they got 20% lower fuel consumption and less emissions of some of the gaseous components that cause air pollution. So it's really looking outside the box in this case, looking at the boxfish. Whale flippers. We know that there's wind turbines all over the place these days, but they don't always operate as efficiently as we might like. So this is a Canadian design change. They looked at the flipper of a whale and how, again, it moves through water. And it's much more efficient than our smooth blade wind turbines we've been using. So they started putting all these grooves on the wind turbine blades to mimic a whale flipper, increased efficiency considerably. We all know about wind farms, and they get various press these days. They're certainly getting a lot of attention as an renewable energy source, but not everybody wants this on their landscape. And we refer to them as wind farms, which is a very human descriptor. What if we had something more like a wind forest? Build trees, so this is an artificial tree with little tiny turbines all over it, just like leaves. And you could put that on streetscapes, and it's not nearly sort of immediately as offensive, or at least more aesthetically pleasing than the standard turbine, and probably much more efficient in that it could work with a few houses or a small neighborhood or one block at a time. Sunflowers. They've got the name because they track the sun, and they move over the course of the day, trapping solar energy. What about mimicking that? And instead of having a field of sunflowers, as pretty as those are, you could also have a field of solar panels that are, again, more aesthetically pleasing and mimicking what the sunflower does all the time. These are already in places like Dubai, which has got a lot of energy, working on a lot of these energy issues as well. And then finally, new building designs. The majority of people now live in cities. We need to look at things a little differently. So start farming in cities. Vertical farming, huge. And it's just doing what we've always done, only vertically. And building buildings like this that mimic termite hills. Some of the most efficient structures that animals have built. They're always cool. They maintain the temperature. You don't need the heating and cooling expenditures that we usually put into a lot of our buildings currently. And bring everybody back to nature. If you're growing things, you're much more aware of nature doing that. So just some practical things. When you're in nature, I know today's not necessarily the day to do it, but never know. Go outside, sit quietly, observe, look at the structures in nature, and think what solutions they might solve. You never know. You can combine biology with any number of things: engineering, physics, chemistry, landscape, architecture, design, whatever. So many options, and more in the future. And just here, I could pass this on to anybody, but if you're looking, there's a website called Ask Nature. It's put out by the Biomimicry Institute. Hundreds of examples in there where we've looked at an organism and seen a practical solution from that. So any questions?